Now we're going to go to the more sophisticated scenario where I can actually detect both states and with the best failure probability. So the best So I have my qubit over here, either psi0 or psi1, and I'm going to have that psi0, psi1 equals S. So that's going to be the overlap between them. And then I send it to my unambiguous discrimination machine, and it has 3 lights on it. It has a light for 0, it has a light for 1, and it has a light for fail. So when we put the qubit into the machine, one of those lights is going to light up, and if the light is 0, it means it was definitely psi0. If the light is 1, that means it was definitely psi1, and if the light is fail, we're out of luck. Now, as I said, the best unambiguous discrimination is the one that minimizes the probability of failure. And it turns out that the minimum probability of failure is in fact just the overlap. So S turns out to be the minimum probability of failure. All right, so that's the case of just one of these things. So now suppose I have 2. So this is going to be Alice here, and this was Bob. So now we're going to add Charlie. So Alice over here, the qubit goes to the first unambiguous discrimination machine. So here's light 1. So that is 0. Light 2 is 1. And this one is fail. And this is Bob again. So let me just label them again down here. So that's the situation. And so Alice is going to send her qubit to Bob. Bob is going to do an unambiguous discrimination measurement on it. And then he's going to send it on to Charlie. And then Charlie's going to do a measurement, do his measurement, and end of story. Though in principle, we could add more. Okay, so let's just arrow. What I'm going to discuss is going to end with Charlie, but there's no reason that it has to. So, in principle, Charlie could also send his on to Dave or whatever name you want to come up with, and the chain could keep going. Now, the first thing is that when Bob does his unambiguous discrimination measurement, he doesn't want to do the best one. If he does the best one, in other words, the one that has S as being the minimum probability of failure, he's going to suck all of the information out of the qubit. So that when he sends it to Bob, the information is gone. I mean, when he sends it to Charlie, the information is gone. So Bob has to do an unambiguous discrimination measurement, but he doesn't want to do the best one. He wants to do one that will enable him to get an answer with a certain probability, but also leave some information in the qubit so that when it goes on to Charlie, Charlie has a certain probability also of being able to identify whether the state was psi0 or psi1. So let's analyze things a little bit more here and see how they go. In order to analyze this, let's think about what happens. So if the state psi0 is sent, so we want to look at Bob's post-measurement states. So if psi0 is sent, okay, so he's going to do a measurement that is, and then he's either going to get 0 or he's going to get fail. He'll never get 1. So if psi0 is sent, he's going to get, let's just call them the state V0 if he got 0, and we'll call it U0. It's supposed to get U if he got fail. If psi1 is sent, okay, then he can either get 1 or fail. So the state that will emerge after his measurement will either be a V1 if he got 1, or it would be a U1 if he got fail. So these are the states that will get sent on to Bob. Okay, so if psi0 was sent and Bob got a 0, V0 would get sent on to Bob. If he got a fail, U0 would be sent on to Bob. If psi1 were sent, then V1 would get sent on to Bob if up to Charlie if Bob got 1, and U1 would get sent on to Charlie if Bob got an F. Now, it's a property of unambiguous state discrimination that the states that you're discriminating have to be linearly independent. Okay, that's a general theorem about unambiguous state discrimination. And we've got a little bit of a problem here, because the state what's being sent to Charlie is a qubit. That has dimension 2. We were looking at 4 possible states. So for this to work, we need that these 2 states are the same and these 2 states are the same. So for this to work, for unambiguous discrimination, for Charlie, we need that V0 equals U0 and V1 equals U. And this can be done. Okay. And so now what we want to do is we want to discuss in pictures. So now these 2 states are the same and these 2 states are the same. So we're just going to use, say, the V notation, since the U's are going to have to be the same. And we sort of want to draw in pictures what's going to happen as a result of Bob's measurement. Now let's look at what the states that get sent to various people look like. So we start with Alice. She sends either psi0 or psi1, and those go to Bob. Bob then does a measurement, and what that does is that extracts some information from the qubit that he is measuring. And so if he gets a 0 or a fail, he sends V0 to Charlie. If he gets a 1 or a fail, he sends V1 to Charlie. Now you notice the way I've drawn this is that V0 and V1 are closer together than psi0 and psi1. And that's in fact exactly what happens, because by removing information from the qubit, Bob makes these states harder to discriminate. So the closer the states are together, the harder it is to tell them apart. So Alice has a relatively easy time telling this. She sends these. Bob has a relatively easy time discriminating psi0 and psi1, but he extracts some information, and that means that the states he sends to Charlie are closer together. So Charlie has a tougher time extracting the information. Now, if Bob did the best unambiguous discrimination measurement, V0 and V1 would both be right on top of each other, and you wouldn't be able to tell them apart at all. So that's why he is going to do an unambiguous discrimination measurement that is not perfect. It extracts some of the information, it makes them closer together, but it doesn't make them lie on top of each other. The perfect one would do that. So what we'll always have that is less than. So the smaller the overlap between the states, the easier they are to distinguish. So these are easy to distinguish, so they have the smaller overlap. because Bob has taken some information out of the states. The ones that are left are harder to distinguish, so they have a larger overlap. So Charlie now measures these, and so what is the probability that they can both get information out of the state? So that is equal to the success probability, the best for the sequential measurement. Success probability is 1 minus square root of s squared. All right. So the so this is the probability that both Bob and Charlie will be able to tell what state L is sent. In the case of single unambiguous discrimination, if you do the best measurement, then this would simply be 1 minus s. But the fact that you've split the thing into two pieces so that both of them can possibly find out, that reduces the success probability. But the point here is that it is possible for both of them with a certain probability to find exactly what state L is sent without errors. So if L is sent size 0, there's a certain probability that both Bob will be able to say it was size 0 and Charlie will be able to say it's size 0. And that's a result of measuring the same qubit twice. Bob measures it, then he passes on the result to Charlie. Charlie measures it. And as a result of those two measurements, there is a certain probability that they can, in fact, both determine exactly what L is sent. So this is kind of a strong example of the fact that measuring the same qubit twice can be useful. This could be useful in a communication scheme. So Alice sends the qubits to Bob and Charlie, and they, with a certain probability, can both determine exactly what she sent. So the conventional wisdom about measuring the same system twice doesn't really tell you anything is really not true. Sequential measurements like this can in fact be useful, and they can in fact be useful in quantum communication schemes.